Good morning and welcome to the second session of the 24th of the 3rd, 2020. I hope that you've already submitted the two do now questions, which you can see on the screen here, because if you have not done that at the start of the lesson, then that's what I'm using to take the roll from the start of the lesson. So please make sure you've submitted these before you begin. So we should just firstly check our answers to make sure that we got these correct. We know what our logarithms look like, being the inverse of our exponential functions. So the first one is just like our normal logarithm. However, because x has been replaced with x plus 4, it has been moved to the left 4 units. Okay, so that would mean that the asymptote would be moved 4 units to the left at -4, and that is the line that this graph has never reached, and it would mean that the graph therefore would go up here and go through at -3. Okay, at -3 and work away across. So y is equal to log base 2 of x plus 4. We would also need to work out our other intercept, which is our y-intercept, and as we know, we find our y-intercept when x is equal to 0. So we could say, if we want, for this one, let's put here, when x is equal to 0, y is equal to log base 2 of 0 plus 4, which is 4. Okay, and this is actually a number. It's asking us 2 to the power of what? It gives us 4, and we know 2 squared is 4. So it would be 2 up. Okay, so that's 2 up there. If you didn't know what this was, if it wasn't an exact number, then of course we could go through and get the emulator and use our change of base, which we'll do in our second question, and change this to log of 4 over log of 2. Okay, so using it either a log or ln button, log of 4 over log of 2. This is base 10 on the calculator. Now log base 4 of 10 over log base 4 of 2, and that gives you 2. The second question that we should have done is to change it to an expression with base e, and we know that we could therefore write that log base 4 of e is equal to log base e of e over log base e of 4. Okay, so remember, changing our base, I kind of just imagine it as like a line going just here, like kind of like this, and then I think it's like log base e of this one, or log base 10 of this, whichever it is, and then log base 10 of, say, 4. Okay, so it always becomes that there. If we then use our log laws, e to the power of what is e, and we know e to the power of 1 is e for this part here, so this would change to 1 over log base e of 4. And our other log law, if we wanted to, in our logarithms, not in our logarithms, in our differentiation section, we have two formulas. This one I will talk about, however, the Cambridge book doesn't seem to talk about this, but I'll bring it up. But the other one is when y is equal to ln of something, dy dx is equal to the derivative over that something. Okay, so let's put that there and go through some examples and work out what that actually looks like. Okay, so our heading is differentiation of logarithms. Okay, so please have this down. Let's get some practice. So the formula is, if we've got y is equal to ln of f of x, that will go to dy dx is f dash of x over f of x. So firstly, we'll check and see if it's actually true. So this is going to mean that if I just have a basic logarithm, e.g., if I have y is equal to just f of x, not f of x, y is equal to ln of x. Okay, we would find that therefore dy dx is equal to our this part, which is in the denominator, so our x is our f of x over is under the derivative of that highlighted part, so over 1. So does that make sense if we draw a function? Okay, so if we had this function, and it is a function that goes through like that, we can see that when x is a really small number like 0.5, if x was 0.5, then our derivative is 1 over 0.5, which is 2. So it does make sense. So if you were half across, because this is at 1, if you were half across, then the gradient at that point is 2. It's got a slope of 2, and that makes sense. It looks right. Okay. We also have the point when the gradient, or when x is equal to 1, when we're at that intercept, and when x is equal to 1, the gradient is 1. So that is, the gradient at that point is 1. Okay, and that makes sense as well, because when we looked at our exponential functions that go up like that, their gradient was also 1 for our e to the power of x, not for the a to the power of x, but e to the power of x, and this is the inverse of that. Okay, so it does make sense. Also, if x became a larger number, like 10 across, then the gradient is 1/10 at that point. So let's have a look at some other examples then for this. So firstly, if we have just a basic logarithm with a different, say, to the power of, just say if it's like our exponential here. So just say we had our log of, say, 4 minus 2x squared. Okay? If we want to differentiate this, we would just use our log, our law from our formula sheet that's saying that this is going to be in the denominator and the derivative of it is going to be in the numerator. So dy dx is equal to, in the denominator it's 4 minus 2x squared, and in the numerator is the derivative of this, which is, as we can see, that's the derivative of this is nothing, and the 2 is going to come forward to negative 4x. So this is negative 4x over negative 2x squared. Now, I probably don't like that format with the negative 4x. I would probably actually change this as well, and I would actually write this denominator, if we want, as also a negative, which is the negative of 2x squared minus 4. Okay, it's still the same thing in the denominator. However, now I've got negative 2x squared, and then negative times negative is plus 4, which is the same thing. However, now I could cancel out these two negatives. I'll just rub them out and write it how I would actually prefer it, like that. So I didn't need the brackets, but that's how I would look at it, like that. Okay. We can also use our product or quotient rule. and answer different questions involving those. So for example, just say we had maybe Eg3 is y is equal to, just say it's x cubed, and then ln, maybe we'll just say x cubed ln x, and then we'll have a look and see what we've got. So this is our product rule question. Okay, we've got a function of the form y is equal to uv, and therefore, actually I think it's on the formula sheet up here, y is equal to uv, and therefore we can use our, I don't like this, I'd rather use v du plus u dv so we don't get confused, but we can use this formula here. So I'll do it the way I remember, but you're more than welcome to just copy off this sheet for that. But we've got this, and we know that u is equal to x cubed. So differentiating u with respect to x is 3x squared, and v is equal to ln x. So the derivative of v with respect to x is 1 over x, and then we can just use v du plus u dv. Okay, so that's going to become v times by du, which is 3x squared. I should write that before the ln x. Okay, plus u, which is x cubed, and then dv, which is 1 over x, and we can see that they are going to cancel out. Okay, so I just wanted to just put that as u dv plus v du, or sorry, v du plus v dv. I was just trying to say it the way the formula sheet does, but this is going to get us now 3x squared ln x, which we can't simplify. I mean, if I raised this 3x squared up to the power here, it's not going to help, it'll just make it more complex, and then plus x squared. Okay, however, now we've got an x squared in this term, we've also got an x squared in this term, so you could, if you're interested, you could put this as x squared by 3 ln x plus 1. Yeah, and you could put it like that as well. So let's have a look and put this in terms of our actual, as a function, just say. So Eg4, if we have a quotient rule question, so just say we had y is equal to, say, ln x over x. Okay, or I'll put this as f of x is equal to ln x over x. Okay, so we know we're going to use our quotient rule. We're going to find what this is u and this is v, isn't it? So u and v. It's always u under top. Okay, down the bottom here. So we're going to look at our u is ln x, and du dx is 1 over x. V is x, so the derivative of v with respect to x is 1. And therefore, if we differentiate this, remember we're not going to write dy dx, we'll just write f dash of x, okay, is equal to v du, so x by du dx, so x by 1 over x, which of course cancels out to just be 1, minus u times by dv, which is 1, all over v squared, which is our x squared. Okay, so what we get is 1 minus ln x over x squared. That's our derivative, and therefore we could go through and see what these actually look like. So firstly, if we wanted to think about what is the gradient at 0, we would know that it wouldn't work because we can't go over 0 here. And also our function is undefined when x is equal to 0. The domain does not include 0 for this. And the domain also doesn't include any value that's less than 0 because we can't input ln of anything less than 0 here. Okay, if I put ln of -1 on the calculator, as we should know, it will just come up as a math error. Okay, because our graph is not defined, as you can see here, for any value that's less than 0. And if I then put this on GeoGebra, let me go to GeoGebra, we can actually graph what that looks like and test to see if these gradients are true. So I'll just put as y is equal to ln of x over x. So this is what the graph looks like. If we see at x is equal to 1, or in this case here, f of 1, I could just say when x is equal to 1, f dash of 1 is equal to 1 minus ln 1 over 1 squared. So e to the power of what gives you 1, and anything to the power of 0 gives you 1, and that's why we get, this is just 1, just there. So the gradient of our function is 1 at that point, and then look how it gets, gradient is, and looks like it's negative, but it's a pretty small number as we're going along. Okay, so if we check that, just say, we say when x is equal to 5, actually I'll put this as x is equal to e because that could be an important one. When x is equal to e, then f dash of e is equal to 1 minus ln e over e squared. Okay, e to the power of 1 gives you e. So the gradient at this point is actually equal to 0. So that's 1 minus e is equal to 0. Again, if we had this function just here, and I asked you to find when it had zeros, it would be when the numerator is equal to 0, and solving when 1 minus ln of x is equal to 0 is the same as therefore saying when ln x is equal to 1, and that would mean that it's when, you know, if I raise these both to the power of e, it's when x is equal to we could do that there. Okay, so that's why we've got our asymptote, or sorry, not our asymptote, our stationary point when e is equal to when we're at e just there. Looks like it. Okay. Okay, and by the look of it, it looks like we could actually check to see what kind of stationary point it looks like. I have a feeling it's going to be a maximum turning point, but we could check that. Remember, we'd use our table of signs. We've just got a gradient, we've done a gradient before it and said the gradient is 1. If I check a gradient after e, so for example, I could use 3 because, as you know, e is equal to 2.7 to say. So if I used 3, then I would get actually a negative number because 1 minus ln of 3 is a negative number. So it's going to be negative this over 3 squared over 9. Okay, so I could use this table of signs to show that the gradient is going from increasing to 0 and into decreasing after it. I'll stop there. I'll let you look at exercise 6G for this session. What you must do is submit your work for this session before moving on to session 3. I need to check the roll at the start of the lesson, which is why I needed your do now, and I need to check your roll at the end of the session to make sure you've done the work, and that's why I need you to submit what you've done this session before moving on to session 3. Have a good day.